Good morning, everyone. How are you all? We shall start very shortly. Let me just get the PowerPoint up. Any questions so far from the previous lecture on the introduction to deep learning networks? So today we will continue with the topic on deep learning. And later on, you'll see that actually it's a continuation, what we have learned so far, except that maybe as there are some, of course, there are some differences. Any one of you, I think you guys are SEM 1, I think you know in the SEM 2. Any one of you keen to come back to the campus, or you're comfortable staying where you are? Right? I think you look at the news. I think the country is moving towards that direction, at least in October. Okay, so I think you can hear me. Kenpai, thank you for responding. At least I know that at least some of you can hear me. So let's continue with the topic on the deep learning. So in particular, we'll look at one particular model of your deep learning networks. Actually, I think there's a bit of hype about deep learning. So I think you'll see that there are, of course, it's not as simple as that. You can also have difficulties of getting the deep learning network to learn. So you need to do some tweaking, but later on you see that basically it has replaced some of the things we are doing with the other processors, and then included into your new networks, and let the new networks perform those functions for you. Okay. Before that, I just made an announcement. Since now we are in the towards the tail end of your semester, and I looked at it, I think I would like to have one extra hour, probably on the next Wednesday. So we will start at 9 o'clock instead of 10 o'clock. None? Okay. None, I think maybe didn't realize his camera was turned on. So just a reminder, we will start the lecture next Wednesday. No problem, Haonan. Just that maybe some of you do not want to be seen. I think some of it happened to me before. Either your camera was turned on or the microphone was turned on unintentionally. So no problem here. So don't worry about that. Back to this. So next week the lecture will start at 9 o'clock. We will still continue until 11 o'clock. So with those extra hour, I will try to cover some of the. I will use that probably that early 1 hour slot. We actually maybe do the tutorial so that in the last week 14, so we will actually combine all the week 14 tutorials into the maybe some of these tutorials, because if you wait, if you follow the normal timetable, it will drag on. So it will drag on. I think it's not so nice. It will drag on, and then so we will want to have that. I would like to have that on next Wednesday. So just a reminder, I will send out the details later on the Google Classroom. This is a quick announcement for you to at least schedule your time for next Wednesday to start at 9 o'clock instead of 10 o'clock. Okay? So we will continue with this morning's lecture. So we'll talk about the deep learning and especially the convolution neural nets. Again, this is just a basic introduction on the topic itself. So what we hope to learn from this 1 hour lecture. So we will be introduced to the convolution neural net. So if you look at the history of convolution neural nets, actually has been around for a long time. When people started to explore, people started to investigate neural networks. So to me, it's just another form of neural networks, except that this one has maybe able to do certain things, and people get excited with the ability of such convolution neural nets to actually do some interesting things, as you'll see later on in the last part. In this lecture, we also look about what to mean by cooling. And then, of course, before that, we have to go into the actual, the key processes, the key techniques, or kind of the key functions of your convolutional neural nets. Then later on, we talk about cooling, and then what we mean by dropout. This is actually even last year, as recent as last year, there has been some work done to actually look at dropout, as you see later on. And then later on, we just talk a little bit about show some of the applications of CNN. But of course, as I said before, because this is more towards the leading edge of research, so now we're at the edge of research, so the actual field itself is changing very fast. So some of these things I show you today may have been outdated. There may be some other new forms of applications, and I believe some of you are also doing that in your FYP. So you also will be, or rather you and your supervisor will also be contributing towards the field of convolution neural nets, or CNN. Okay, so far so good. Now, let's look at consider learning an image. How do you learn an image, right? If you look at the image here, as shown down here, this is a simple picture of a bird, little bird standing on maybe a branch or a stick, right? So now, if you look at the bird itself, the motivation is for us to maybe recognize what the species of this bird is. So if you ask the expert on the bird watcher, they call it bird watcher, they will tell you that maybe one of the things you need to look at is the beak of the bird. Now, so if you look at the beak of the bird in this picture, such patterns are much smaller than the whole image. So you can see, I'm only interested in the one part of your picture, right? So if you give me a whole picture, I'm only interested in one part. This is normal, right? It's again, if you reflect back of a human yourself, if I ask you to spot certain things, you find that I don't need to look at the full picture. I want to look at only one part of the picture. So we will then only look at one part of the picture, and then we want to maybe use that small part to actually let us know. I can see here, what is this, right? I think a large number of you have actually gone through the tutorial. You see this is a representation, maybe scientific, if I may say so, a scientific or engineering application representation of your right, your summation, and then your non-linear transformation. So this is here. So I want to look at only this part. So this is what I want is actually a design and implement what we call a beak detector. What's the color of the beak? What's the shape of the beak? What's the texture of the beak? So on and so forth. So this one will detect the beak. So we can then represent a small region, because what's the motivation? Why are we doing this? Because the motivation is we can represent a small region with fewer parameters. Imagine if you have to represent the whole image here, right? There will be more things to represent, larger number of parameters. So again, this is, I think we talked about this before. Now, what does this remind you of? If we have many parameters to look at, right? So this will be your curse of dimensionality. If you have too many dimensions, your parameters to represent a picture, right? You find that the scientific methods, or your, what do you call it, your AI techniques will have difficulty due to the curse of dimensionality, because it's actually, once you increase the dimension, it's actually the level of difficulty is not linearly transformed, right? The difficulty is not linear. If you have 10 features, doesn't mean that you have 10 level 10 of difficulty, right? So that is remember, we talked about this before. the curse of dimension. So the motivation is, if you can represent, if you're only interested in one small part of your whole image, I can then process that smaller picture and resulting in fewer parameters for my AI to actually process. Right? Now, the other problem is that some patterns appear in different places, right? And of course, they can be compressed. Now, the question now is, what about training a lot of such small detectors, and each detector must move around? So the problem is, if I want to look at the picture for me to identify the bird, right? You will tell me that I'll look at the color of the body, right? And basically maybe the shape of the overall shape and the size of my bird here, or my object in this image. So these kind of patterns appear in different places. They're not at the same places, right? So again, this is because that's why we're here, right? If it's so simple that you have only one region to look at, right? You don't need engineers, you don't need scientists, right? And so simple, everyone can do it, like sweeping the floor. But at the same time, such patterns can also be complex. So the challenge of the solution, the obvious solution seems to be, if you can train your detectors, right, by moving around, by having a few of these detectors and then moving them around in your image, right? There seems to be a logical solution. So again here, in addition to your first image or picture of a bird, you see in the previous slide, there's one question, Poon Kiong. Or maybe you accidentally turn on your mic, is it? Okay, maybe it's accidentally turn on the mic. Are you asking a question? No? No one? Okay. So the other thing is that you can see here, my mic, talking about this. So we have this little bit here. So now we want to detect the birds, right? Okay, are you all right? Or is it just only me hearing Poon Kiong? Okay, thank you, Poon Kiong. So okay, yeah. So yeah, back to here, right? So we want to detect the birds. You can see here, if I want to, first of all, I want to, let's say, for example, I want to identify the bird by looking at the beak. You can see here, even for this simple example, you can see that the beak itself is not at the same place. So then again, this is one of the problems. So of course, you want to have an ideal situation where the birds are always at the same place. But you tell the photographer to actually photograph the bird so that's exactly the same place. So there's, of course, that's not easy in the real life. So because of the real life conditions, you find that when you design your system, actually it gives you a lot of headache. So here, for example, here we have a big detector here, and then this is so we say that I want to have a upper left big detector at the upper left section of my image. So then this one is then you have another one because when I take my photographs, I make sure I take photographs where the bird's either at the center or it is something like move to the something like that, move to the upper left side. So for me to detect the bit later on. So when you actually design your experiment, you must be aware, you must be conscious of how your system, your intelligence system will process the information. You can't just go in there blindly. So the experimental data collection also has to be planned. So now we have two big detectors, one at the upper left and one at the center. So they can be compressed to the same parameters, right? They can be compressed. Now, what do you mean by compressed, right? Somehow the picture is there, right? It's an x by y dimension, even though it's small, right? X1, y1 here is smaller than your x by y in the original picture. So it is some sort of example to tell you that this is some sort of compression. At the same time, even x1 and y1 is smaller, I can still compress this further. So if you imagine the x1, y1 is actually in terms of pixels, it's going to be 200 pixels. So imagine your 100 by 100 pixels, and you stretch it up into a vector. So it's a huge number of pixels to process. But if I can compress this, I can extract certain features, certain characteristics out of this. I can then have a smaller number to process. So this is actually what we meant by compressing to the same parameter. So again, within this window, maybe for example, I take the color, the what do you call it, the median color intensity of my window. So one feature, right? So again, if you do that, both windows will share the same parameters. Follow so far? So I'm going to go a bit slowly here. Right. Now, so let's go back to, let's stop there for a moment, right? We have talked about this. Let's stop there for a moment and go back to our neural networks. Now, first of all, what are CNNs? Of course, I would say equal importance, what do you call it? What's the word I'm looking for? Equal in terms of the understanding. Fame, the one is fame, full fame, right? Now, if you talk to not maybe a non-engineer or non-scientist, CNNs are regularized versions of multi-layer perceptrons, right? So these they are not an engineer or a scientist, they may not know what's CNN. So to them, CNN is our central news network, right? The American big giant, the American big broadcasting company, right? So again, but for us, working in the scientific field, we know that what are CNNs? So CNNs here, we know that they represent convolution neural networks. And what are they? They're actually regularized version of the multi-layer perceptron. So again, back to the same thing. They are nothing more multi-layer perceptron with multiple layers using the same processors we have been talking about for the past few weeks. So of course, this one, right? So I think I will maybe I'll just go through quickly. I think we've gone through this before, but just for completeness, we'll go through that for the definition. Now, this is taken from Wikipedia. So as you can see, from now on until the end of this semester, you find that the topics that are covered actually are more of the advanced topics. So some of these content taking them from various sources. So multi-layer perceptrons usually refer to the fully connected networks. That is, each neuron in one layer is connected to all neurons in the next layer. So it's fully connected. But of course, this can be argued. What do I mean by that? Because even though you connect point A to point B, in point A means in your earlier layer to your next layer in your point B in the next layer, right? They go through a weight, which is your synapse. Remember your synapse and your weight system. Now, during the training, the weight value may drop to become 0 or very, very small. So what does that mean? It means that there's no connection from A to B if that happens, because it all depends on your application and how you want your network learn and what it's supposed to learn. So this is actually quite a fine point here. Yes, you connect point A to point B from one layer to the next, but during the training, that connection may not be useful enough. So the network will actually drop that layer or drop that connection. Sorry. So the fully connectedness of these networks makes them prone to overfitting data. What do you mean by overfitting? You only learn about apples and oranges, right? You are very good at looking at apples and oranges. So everything you see is under apples or oranges. But what about pears? What about watermelon? What about durian? That is, in a way, a simple way of explaining to you what you mean by overfitting. So you kill it in the sense that you actually force the network to only know about the apples and oranges. Other fruits, you don't know. So what you call overfitting. So you actually drown your network with just one type of data. So it's overfitting the data. But of course, as a result, it's able to give you wonderful results. Assuming it's only apples and oranges. But if you bring in a new piece of data, pears or durians, it will not be able to give you the answer. Now, typical ways of regularization include adding some form of magnitude measurement of weights to the loss function. So this is how you can regularize your multi-layered perceptron network. Now, this is your multi-layered perceptron, multi-layered network. Now, CNNs, on the other hand, take a different approach. This is towards regularization. That is, they take advantage of a hierarchical pattern in data. Now, this is a new idea that when this person actually designed or proposed the CNNs, they want to take a different approach. They want to take advantage of the hierarchical pattern in data. There's a hierarchy in the data. An example, more complex patterns, right? You bring together the different complex patterns using smaller and simpler patterns. This is the whole idea behind CNNs, right? You break your large image into smaller chunks, smaller pieces, right? Because they are simpler and they're smaller. So therefore, on the scale of connectedness and complexity, CNNs are actually on the lower extreme. So this is a very general description of CNN. They take advantage of the hierarchical pattern in data. So your pattern, your data, in your actual images must have hierarchical pattern, right? And then you break them into smaller chunks, smaller parts. As a result, you're able to process smaller pieces of data, right? And then in a way, you actually minimize, right, your exposure to the curse of dimensionality, right? So this is an example of a smaller network, your CNN, right? We know it's good to learn a small network. We always know that it's always small is good. Small is beautiful, not large is beautiful. Beautiful, if it's large, takes a lot of time, and also takes a lot of effort to actually design such a large network. Now, from this fully connected network model, can see here, I have two hidden layers. No, I have three hidden layers before I connect to your output layer. So again, you can see here, this is your, it will remind some of you of your multi-layered perceptron network, multi-layered network. Now, for this fully connected model, do we really need all the edges here, all these connections, all these edges here? So can some of these be shared? So those are the questions if you look at. So again, what does it show you? It shows you that in order to be very good at technology, you need to have very, actually not true, not even everything in life. It's all about analysis. You see something after looking at the data, you see something other people do not see, right? And that will give you the edge. It will give you the advantage. So I always like to go back to basics. So when we talk about convolutional neural networks, why do we choose the word convolution and not Achong or Ahmad or Samuel, for example? Why do we call it Samuel neural networks, SNN, right? So when we choose the word convolution, right, there must be a reason why. So let's go back, let's stop for a moment, pause for a moment and look at what we mean by convolution. So I choose to take the Merriam-Webster dictionary. It's a quite established, well-known dictionary. And they define convolution as a form or a shape that is folded in curve or tortuous bendings. So imagine, if you look at it, one example would be used in the word, in the phrase, in the sentence of convolution of intestines. So our intestine is actually tortuous or curve, wrap around, twisted in a way. So of course there are many, there are also other types of other definitions, other explanation of what we mean by convolution, right? So one of the regular ridges on the surface of the brain, especially of the cerebrum of the higher mammal. So if you have seen the picture of the exposed brain, you probably understand what we mean by this definition of it, right? So I will not go into the next one. So basically, you give the idea is a twisting or curve of your structure. Now, let's start by looking at the convolutional layer. So a CNN is a neural network with some convolutional layers. Now we understand, right? So now we know why we choose the term convolutional neural network. So a CNN is a neural network with some convolutional and also of course, and also so it doesn't means that we have convolution layers. You can also have other layers. So a convolution layer has a number of filters that starts convolutional operation, right? So a convolution layer would have a number of filters. A number of filters are not necessarily one, right? That does this convolutional operation. It will just basically twist. It will transform. If I may use the word transform, your input data into some other form. So this is actually go back to here, the twisting, folding, right? So this is so in this case. Go back to our example. If we want to build a network to identify birds by looking at the beak, so we have a filter that actually part of the beak detector. So what is convolution in terms of in purely mathematical terms, right? So now we are trying to explain convolution in the mathematical term. So a convolution is a function derived from two given functions by integration, which expresses how the shape of one is modified by the other. So basically, if you look at it this way, it's just a convolution or transforms the earlier shape or input into another form by having this convolution process. Right. So this is one definition of the in the mathematical field of convolution. So far, so good. Any questions so far? Okay. Now I'll go a little bit about the actual convolution process. So let's look at it and see how it works. So you place it over your convolutional process. You place it over input image. For example, beginning from the top left-hand corner, within the borders you see demarcated in the figure. Right. So I'll go to that picture later on. And then you count the number of cells in which the feature detector matches input. So you have your feature detector, and you try to match the trying to detect certain features. In this case, we're trying to look for the beak. So you can also look for the tail. You can also look for the eyes. You can look for the legs of the bird, for example. Now, the number of matching cells is then inserted in the top left-hand cell of the feature map. You then move the feature detector one cell to the right and do the same thing. So we start from the leftmost corner and then you move from say left to right. Of course, you can also do from right to left, but right, this is for convenience and this is simple and common thing to do, left to right. This movement is called, this one is actually a missing sign here, and since you're moving the cell, we call this a strike, called a strike of one pixel. So we move one pixel at a time. For example, this is your feature detector. So you place it over this window over here, as you see later on. Oh, sorry. Hang on, my system is slow. Okay. Now, when you find in this, what you find in this example on the next page is that the feature detector's middle left cell with the number 1 matches it to the cell that is standing over inside the input image. So this is your feature detector, and you will match this one. Right, so you can see here all are 0. So even though you have this particular pattern here, right, 1 over here, 1 over here, and 2 ones over here, but over here they try that all these are 0. So all these are irrelevant, so to speak. Right? Okay, so that's the only matching cell in right or 1 in the next cell in the feature map, and so on and so forth. So we have to. I think we'll later on we'll go through this. I think we'll become clearer. So all these words are not very clear to you. Now, after you've gone to the first row, right? So imagine you can see here, this is my cell. This is a 3 by 3, and then you move. And after finishing it, you then move, right? You then move over to the next row, right? So first step, of course, you move to this row, right? Left to right, and then after that, this row finished, you move to the next row. That's how it does, right? Move the next row in, and then go through the same process again, right? So you can see here. So the how do I do this? I need a pen. Okay, so you can see here. First of all, I look at this particular. If I say to use the word quadrant, right? This is a 3 by 3. So you can see here. Now, what do you see here? So basically, it's what do you call it? Exclusive OR. This is exclusive OR. So what it means? So if you compare, right? You only compare for differences, right? Differences you get a 1. Right? Remember your exclusive OR, your 0, 0 is a 0, right? 0, 1 is a 1, and your 1, 0 is also a 1, and your 1, 1 is a 0. So we compare. Now this fella here with this fella here, what do you get? You get 0, right? Then you add up, you add up, right? So over here, you do the same thing. This one, this fella and this fella, right? So you can see here, there's only a 1 here. So all these are zeros. So nothing happens, right? But also only a 1 here. 1 and a 0 is still a 0. So you get a 0 over here. So this is your first quadrant. Now, if I do it on the next one, okay. Now if I do it on the next one here, to give it a 1. So I move it to the right hand side by 1 cell. This is a straddle by 1, remember? So here, a stripe of 1 pixel, right? So move it to the cell, to the right hand side, right? And then you can see here. So now what do you have? So you can see here, this one matches. Sorry, this is not actually not this is 0, 0. This is a multiplication. Sorry, it's a multiplication. So this is multiplication. Because if I have 0, 1, 1, 1 will be a 1. Right? Sorry about that. So this is the 1, 1. So give you a 1. So the rest is what? The rest is all zeros, right? So here and here and here. Right? So all these are zeros, except for this fella here. So you place it over here. Right? And you process it to so yeah, 1, then 2, 3, 4, 5. I think that's it, right? 5. Right? So you can move it maximum of 5 times because the last one is over here. So again, this one here, this is actually in a way same as the first block, because there's only one at the center here. Right, center here. So again, nothing happens. So you still get a 0. Right, and then you repeat. Right. So you have 1 row, 2 rows, 3 rows, 4 rows, again 5 rows. So you get a 5 by 5. So what do you see here? As we said before, you have done some sort of compression. Yeah, compression, right? You have done compression by reducing your initial image. This is how much is it? 3, 4, 5, 6, 7, 7 by 7, right? To just 5 by 5. So this is your resulted output after your process using this feature detector. Right, filter. So reduce it by this. Okay. If you continue now, so now if you have a 6 by 6 image itself, so we have here. Now we want to do a different image and see how it works. So you can see here I've highlighted all the ones inside in this 6 by 6 image. So now I can also apply, right? Remember we said this before. It need not be just one filter. It can be several filters of your choice. Right? You can have a number of filters. So in this case, we choose to actually have 2 filters. Right? And know the filters here, of course, the filters up to you to design. So there's also a bit of art involved to actually come up with the right design of filters. So in this case, you have the filters instead of 1 and 0s, it will be basically sign function, basically a 1 and a -1. So again, notice that the ones here are actually located at different places. So for some reason, you want to put them at different places, right? So you can see here. So you apply this one, will give you one set of output, your feature map. If you apply a different filter, you also end up with a different feature map. So you have two different maps. Feature map if you have two different filters. Of course, you can have many filters up to you to design and use. Now, these are network parameters to be learned. So once you have transform or convolute your input image using these filters, so the network then has to learn the output of this from this convolutional process, right? So basically, each filter detects a small pattern which is 3 by 3. Again, what's the size of your filters up to you to design? Normally, it's a odd number of pixels. So if we look at the first one here, right? 1 minus 1 and here, right? Oh, it's not the same, is it? No, not the same, is it? Okay, here. So we pass it through the first quadrant over here. So again, you do a multiplication, right? Dot product, you get a 3. Now, how do we do that? So we look at it. So we have 1 minus 1 times of 0 becomes a 0. So this one will be zeros because it's 0, right? And this is also 0. So this is no effect, or you get 0. You get 0 here, you get 0. So you only get this diagonal. So diagonal, what you get? You can see 1 plus 1. So it's 1 plus 1 times 1 times 1 plus 1 times 1 second one. And then the last one, so you get a 3 over here. Right? That is using a stripe of 1. Right? We talked about this before. So with stripe of 1, I moved it. Basically, it means that what is your step? Right? The step of moving to the right hand side. So you stripe of 1. So your middle now move to the right, and then to stripe of 1, and then you actually do the same, repeat the same process. Now, why 1? Why not 2? Why not 3? There's a reason behind that. If you take a stripe of 2 or 3 or more, you reduce. You have lesser. Focal size is smaller, as you will see later on. If you stripe of 1, of course, you have more things. You have more details, but of course also means you have more computation or calculation to do. So here, the next one is do the same thing. So here, my okay. So see here, the next window here, I have here, and here. So I only have here. So let's look. All this is 0, not counted, not counted, not counted, not counted. Okay, so I only have this 3. Now what do I have? So minus 1 times 1 get minus 1. Then you have this one times 1 again, minus 1. The last one is 1 times 1. You get a plus 1. So that's why you get a minus 1. But it's very simple. So one of the ideas is that the actual process, the convolutional process, can be as simple as that. Right? So we actually convolute your input image to a smaller output. Now, if I use stripe of 2 now, what does it mean with use stripe of 2? As we show here, first of all, you still do the starting from the top left hand corner, and then you perform the same calculation. You get a 3. Now notice here, I'm now moving to, I'm now moving, I move 2 cells or 2 pixels to the right. So you bypass. So it's a smaller processor. It's actually, you have less things to process, so it's faster, right? But of course, there's no free lunch, so you have to suffer because you are now missing certain information if you use a stripe of 1. So this one, so you get to do the same thing here. So you can see here, all these are 0, 0, 0, 0, nothing here, nothing here, nothing here. So we have also only this. So you can see here, all these are 1, all these are minus 1. So we get a minus 3. Now what is this minus here? So this side of 1. Now if you build, right, your side of 1. Okay, so what you end up with. So from this side of 1, you find that 1, 2, 3, 4. Yeah, 5, 1, 2, 3, 4, right? Because the last, since it's 3 by 3, the last one will be sitting here. So that's how you end up with. So this is a 4 by 4. From 6 by 6, you get a 4 by 4 set of features for you to process. So this right? So you can see here, that's how you actually look at it. So because the rest are zeros, right? So you only get that, right? So you only get that here, right? Now filter 2, basically repeat for each filter, if we do it for strike of 1, right? So you can imagine if you will basically imagine that if you have many filters, you will be placed on top of each other, shown here. So this is a convoluted output from the second set, and this will then become your feature map. So the actual process of feature extraction is no longer done externally. It's done performed by your convolution neural net. So that is all integrated, if you like, into that neural network stuff. So now you have two 4x4 images forming a 2x4x4 matrix, right? So this is your output after the convolutional process. Now, for the color image, which has 3 channels, let's look at a simple example where your color image is using the RGB, not any of the other less popular or less well-known image format. We use RGB. RGB has 3 channels, right? So now, from the so if we were to, of course, the intensity level for each layer will be different. So what you have will be a representation of the color intensity for each layer will be 3 layers, right? Because your red layer, your green layer, and your blue layer. So if you use 2 filters, you end up with basically 6, isn't it? Right? You have a total of 6. Sorry, is it? Filter 1 will give you for each of these one layer. So you have 2 filters, you have 2 for each, so you have 6 layers as a result, right? Now, let's look at discuss the convolution versus fully connected, right? The fully connected network here, right? If you have just take the one layer, either the red or the green or the blue, right? So this is we stretch into a single vector and then you process it, right? Using your neural network. Now, for this convolution neural net, after you convolute your image itself, you then have a smaller based on the 3x3, 2 filters. You have this what called 4x4x2, right? So you have 4x4x2 extracted features for you to process, right? So this is 2x4x4 is what 4x4 will be 16 is 32. This is 2x6 32. This is 6x6 36. But so you get a bit of a trade-off, but it's smaller. But of course, this is what they call it. This is not much smaller. But the thing is that this is actually this one contains more information compared to this one. I will argue that way. This one contains more information because it's actually processed these abstracted features from it. So it's actually a different representation of the input system. So as a result, this one should give you better results compared to this fully connected, right? So if you look at the whole CNN now, if I want to detect this cute little animal, the cat, right? So you have your normally in addition to convolution layer, you also have something called max pooling. So these are the basic ones. Convolution layer, max pooling, and then you repeat this as many times as you like, right? And then you after you finish that, you then flatten it on top of this later on. Then before you pass the output to your fully connected feed-forward network to identify whether it's a cat or dog. So these are additional processes before you still go back to your what do you call it, your well-known, your familiar fully connected neural network. Now, so we have now introduced the concept of max pooling. What is max pooling? So max pool after you look at max pooling. So this is what, right? Remember, this is your output from your convolutional layer using one filter, right? So if you use 2 filters, you have another one, second filter based on this design of the second filter. Now the idea of max pooling, you can see that just now we talked about this before, right? You can see that this is about what 4x4 is 16. 16 times 2, 16 times 2, 32. This is 36, right? So in terms of the actual trade-off in terms of the actual size, right? This is only about 36 and 32, only 4 neurons smaller, right? But now if you have this max pooling, basically max pooling, if I do a 2 by 2 max pooling, what it means? It means that I take the maximum value in the pool, I take the maximum value of the pool, right? So the sign has to be taken into consideration. So in this case, this is my larger value. So this one will be 0, this one will be 3, this one also will be 1. Now, how about here? This will be -1, this will be 1, this will be 3, and this will be 0. Right? Oh, sorry. Why? Oh, okay. This one is all -1, doesn't matter. So you pick randomly, pick anyone. Right? So simple, isn't it? Max pooling. Now, what happened here? The idea is that you're able to now reduce your 4 by 4 into just 2 by 2. Right? 2 by from 4 by 4, reduce to actually in a way there's also a bit of, you can call it compression as well. Now, why do you want to do pooling? Basically it's a process of subsampling, right? Subsampling based on the mass of 2 by 2. So in a way it's some sort of masking, right? So it's subsampling. You subsample the pixels will not change the object. That is the theoretical foundation of that. So subsampling the pixels will not change the object. Still the object, the information of the object is still there. Okay. So if you were to this is a explanation to show that this is an initial picture of the bird. Now, if you subsample it, it's actually smaller, but it still represents the bird. That is one way of looking at it. We can subsample the pixels to make the image smaller. Right? Remember, we said this before. Always come back to the motivation. We are trying to avoid the curse of dimensionality. Because when you have a large number of characteristics or features to process, you find that you end up taking a long time to process it, which is not acceptable, right? So we're always striving to have a smaller pattern to process. So again, because of this subsampling, it's not one-to-one, actually, because it's subsample, right? To this process of convolution and also your max pooling, right? We can keep repeating this, right? Of course, this one you may not see the advantage of. You may not see this clearly in this small image. Only say maybe what is it, 6 by 6, isn't it? 6 by 6. So, but if you imagine in terms of now for the normal picture, it can be 1,000 pixels by 1,000 pixels. So as a result of that, I can repeat this to end up with a smaller smaller pattern, the smaller matrix to work rather than having a large matrix to work. So far so good, right? So again, I think there will be some questions, but hopefully you all have the courage to ask me later on. So now, the CNN compressors are fully connected in 2 ways, right? It reduces the number of connections because when there are smaller number of pixels to process, you have a small number of connections to make as well. Then those share bits on the edges, and again, because of the additional process of max pooling, right? You then again able to reduce your complexity somewhat. After your convolution, you do a max pooling to subsample it further. So here you can see after convolution is get a 4 by 4, right? 4 by 4, and then the max pooling only 2 by 2. So now instead of 4 by 4, 4 by 4 by 2 layers, right? So now we have doing 2 filters. We have now 2 by 2 times 2. 2 layers, you can see it's 2 by 2, 8 on it, right? New image, but smaller, which is back to this concept of subsampling, right? So you have the smaller. So each filter shown here, so each filter will be a channel. So you have multiple filters, you have multiple channels. But of course, later on you can still combine them to actually do your classification. Right, you can see here. So this process here, convolution, max pooling, convolutions first, then you repeat as many times as you want. Right? The image from here, another one smaller than original, and then number of channels. Number of channels is the number of filters, as you've seen just now. And you can also process it further as many times as you like, right? And then after that, you flatten it. Right? So now, what do you mean by flattening? What's the process of flattening? Right? Very simple. So you have two layers here, two channels here, due to your two filters. And after max pooling, you get a 2 by 2 by 2, right? It's a 2 by 2, and since you have two channels, you have two. So 2 by 2 by 8. So we have 2, 4, 6. So you flatten it again in the order that you wish. So in this case, you can see here 3, 0, 1, 3, 0, 1 minus 1, 3, 0, 1. Where is it? 3, 0, 1 of this bottom here, right? This one is 3, 0, 1 minus 1, 3, 0, 3, 0, 1 minus 1. So this is actually flatten it into a vector. From this vector, then you can put it to your classifier to classify. Right? Then you have your back to your fully connected feed-forward network. So there's no magic, no special thing about it. So go back to your your familiar fully connected multi-layer server example. Right? And the first is you can have many layers now. We'll come to that. Now dropout. There's another idea here. Dropout here is that you basically randomly shut down a subset of units in the training process. So after training, you find that some of these neurons here are not so useful, are redundant, right? You can drop some of these neurons. You find that you have less things to process. So that's the advantage of that. So in this case shown here, I've shown that these are the neurons here are dropped out, removed or reduced or eliminated. Then you have a sparser representation of your network itself. Now, it is a different net each time, but all nets share the same parameter. So once you have a dropout, it's in a way the same net, right? So, sorry, but the nets of it is you share the same parameters, but the net is now reduced. Right? See here, reduced. So a net with n units can be seen as a collection of 2 power n possible thin nets, all of which share the same weights. Now, a test start is a single net with averaging, and as a result of this dropout process, it avoids overfitting. But the challenge is, that's why you can see here back here again, we randomly shut down. So again, now you begin to see why the seeded random number generator is so important. Because if you are trying to debug this system, right, and you find that you try it one time, and then it crashes for some reason, you're not able to do that, and then next time you try again, you can't seem to find the same error because it has you're down using a different random number, so the actual neurons that are eliminated or reduced or eliminated are different, right? That's why it's important to have a seeded random number, especially for debugging purposes. Now, I think we come to the end now. We're looking at some of the examples, how we can use that. So if you were to, CNN has been used successfully in speech recognition. So we actually represent your speech. How do you do? How are you? For example, that is an example of a speech and recognize that speech, right? So who said the same phrase? Open the door, open sesame, for example, right? So I want to do that. So this is over time, and this is you actually transform your speech signal into a frequency domain. And then you can see here, if you were to visualize it using color, find that it's actually this part of the speech actually can be represented as an image. So once you've done that, you can then go back to your CNN to process it. So again, you process it, right, frame by frame, right, and again you move. Even the one frame, one window here, you process all the pictures, all the part of the this image itself in your spectrogram of your speech signal. So this is actually, now you can also do that in a text classification. What is the what do you call it? What is the text the page is trying to say, right? So we say, I love my new iPhone. And this is a little emoji here, right? So again, this is if you scan a picture of your A4 paper, when you have the word I love my new iPhone, right? Again, this is one example. You can also do that for your handphone, the screen itself, or other things. So this is actually how people have done it, how people have used the CNN in your text classification. Okay, so I think we're just about nice. I think about a couple of minutes left before we end. So this is the final part of your deep learning networks, whereby we look at the convolutional neural net. Of course, what we've shown so far is actually the basic part, the basics of your simplest of all your convolutional neural net. Right? In the deep learning, I think as many of you know, it's actually more than that. There are other types of deep learning networks, and of course, we only look at the one example, and then we must understand better what is your deep learning neural networks. So what we have not done is, what we have not said about this part here. This part here. So this part here actually, now with the convenience and also accessibility to cheap GPUs, you can have many of these layers to actually train your network to learn the patterns after your convolutional process and your max pooling and your flattening of your pattern itself. Oops, sorry. So we talk about pooling, we talk about dropout. Here also in the pooling, we also talk about a little bit about your max pooling. This is your convolution processes using different filters. Of course, the trick is actually to find out what filters work for you. So I think there are certain examples of your filters that will work. And the good news is I think many of you are using maybe your pre-trained network. People have done the hard work. You just maybe use that pre-trained network, and then you do some sort of refinement on top of those trained networks for your application. So in the previous slide, we talked also about a little bit about dropout, and then we've shown you just three examples of CNN in the 3 domains, which is your portrait image, looking at the birds or a cat or a dog. Then we actually apply the same concept. To recognize your speech recognition, whereby the actual speech itself, the audio signal is transformed into a spectrogram. So the spectrogram is now image. So with that image, I can now use the same processors that I use it for images in the CNN to recognize who is saying what, right? And then the last one example will be in terms of text classification. Again, same concept. We transform your text into an image and then use the same processors in your CNN used previously in image processing to process my text. So those are 3 examples. Now, one thing to notice here, what is it? The main thing to notice so far is that it works very, it works very well with images. So normally you do not work with numbers. You actually work with the image. Of course, the image itself can be the intensity levels of the image, as shown over here. So basically, as you can see here, if you're able to transform your data set into image, then of course you can use these processors. CNN works very well with such deep neural nets for images. So basically you have to transform your signal into an image. In this case, my speech signal into a spectrogram. The same thing applies to in terms of text classification. So you can see, of course, there are, I think some other people have actually proposed some other types of extra tools to actually do your processing for that. Okay, so with that, we completed the whole topic on artificial neural networks. We have seen the simple perceptron before we move on to the multi-layer perceptron, and then what we can do. And then we also look at if you remember, the multi-layer perceptron, the multi-layer networks have basically they represent a class of feed-forward networks, whereby the input information is actually move one side, one direction to the output, and then only the errors are propagated backwards using your back propagation algorithm. Then we look at the other type of neural networks, which is your recurrent type, which is a Hopfield net as an example. And finally, in this week, we look at the deep learning, introduction to deep learning networks, neural nets, and then today we look at the convolutional neural nets. So that completes the whole topic on artificial neural networks. Moving forward in the next few days, we will look at next few lectures. We will look at some of the advanced topics, starting with your swarm intelligence this Friday, and then after that, if we complete early, then we move on to your support vector missions. Now, these are only some of the topics in AI. Of course, there are other types of techniques involved which are actually found to be useful, and you can see that especially in the swarm intelligence. The scientists, engineers get the inspiration from nature. You're trying to learn from Mother Nature, some of the things they're doing. I think you can see that. So these are the methods that work very well. And in many applications, especially when you do your literature review or the prior work, you find that some of these terms keep coming up. So at least you know what they represent, what they mean. So with that, I'll stop here. Before we go on, any questions or comments? There's something I'm not explaining very well, please feel free to ask me again for me to clarify, because I can only assume that some things you're not clear. I will explain to my best abilities. Of course, there's some things may not be very well explained, so I leave it to you to ask me if I need to further explain some of these concepts. Okay, if not, we'll stop here and I'll see you back on this Friday. Don't forget we have this extra. We will start our lecture next Wednesday at 9 o'clock instead of 10 o'clock. We will still so it's something like an additional 1 hour to actually sort of replace the tutorial. So we
continue with this geothermal technology,
right?
Okay.
So
in geothermal technology, actually, we can divide into 3 different